Welcome to our presentation at the virtual conference of eCAADe 2020 Berlin. My name is Ziad Ashur and I'm a PhD student at the Architecture Department in Texas A&M University. Today I will present our research paper titled BIM-Powered Augmented Reality for Advancing Human Building Interaction. This paper is part of an ongoing research of enhancing human physical building interaction, and it's authored by myself and my professor Dr. Wian. Augmented reality has been around for quite some time and has not yet been fully adopted or utilized by architecture and construction professionals and educators in the domain of architecture and education due to the tracking and registration limitations, especially when it's used in dynamic and heavily occluded environments such as construction sites or buildings occupied by people and furniture. So we are interested in registration methods that could perform well in such environments, and we also wanted to explore the potential of leveraging BIM metadata within an AR interface, which can extend our interaction with the physical buildings around us through instant access to information related to building objects like material properties or dimensions of a building component. So the objective of this research is to design an AR application that utilizes BIM model, geometry, and metadata of existing buildings. In this presentation, we propose our first prototype, BIM XR. Our registration method utilizes GPS. It requires the user to start the registration process outside the building where the satellite signals are most reliable. We also took into consideration that GPS accuracy normally ranges from 1 to 5 meters, and it could exceed this number since it's highly dependent on the atmospheric conditions such as cloud coverage and the height of surrounding buildings. So to overcome this issue, we provided translation sliders to manually modify the virtual model alignment with the physical building. Once the virtual model has been correctly aligned, the prototype will no longer use GPS and will only depend on the device's inertial measurement unit, which consists of an accelerometer, magnetometer, and gyroscope. These motion sensors are responsible for determining the user's speed, acceleration, and displacement. To preserve the BIM metadata, our approach was to export metadata in CSV file format along with the geometries in FBX format in order to utilize them in Unity, which is the platform we use for building our prototype. However, for simplification reasons, we decided to reduce the number of building objects in the virtual model by grouping them into larger chunks in 3ds Max before importing them into Unity. And as a result, the typical hierarchy of the BIM components was flattened. Since the exported BIM metadata can no longer represent the newly grouped model, we manually created a table in CSV format containing new object IDs matching the newly grouped model with dummy data such as material and family names. The user interface allows the user to control the alignment when necessary, and also allows the user to interact with the physical buildings through accessing information related to objects of interest. The next slide is a short video of our prototype being used in the Memorial Student Center at Texas A&M University in College Station. We tested our prototype to verify the alignment performance and measure the amount of drift as a result of only depending on the device motion sensors. The results indicate that our prototype can maintain its alignment outdoors, but part of the indoor environment cannot be maintained due to the accumulated errors of the motion sensor calculations. Additional computer vision and artificial intelligence through deep learning needs to be integrated to enhance our method. Architecture education highly depends on experiential learning to link theory and practice, like learning from physical buildings and construction sites. We envision possible uses of our prototype that can enhance the learning experience during site visits or inside classrooms through adding further capabilities like contextual visualization of daylighting analysis and CFD simulations, as well as simulation of building material assemblies and spatial ability training through sections and slicing. Thank you for watching, and please have a look at our paper, and if you have any questions, feel free to contact us.